Hello, I'm Dan Anderson, Associate Professor and Extension Specialist in the Ag and Biosystems Engineering Department here at Iowa State University. And today, I'm going to talk about everyone's favorite topic, manure. Specifically, I'm going to talk about the impact of uncertainty and application variability on decision making. So the goal here today is really to talk about how those things that we have trouble controlling, hitting the exact rate, knowing the exact nutrient content, getting uniformity across our toolbar, impacts how we should utilize and think about manure as a fertilizer for our fields. I won't presume to have all the answers. I'm going to try and talk to you about at least some of the things we've seen, some of the things we're trying to figure out, and potential places you can capture some value. But anytime you're talking about uncertainty, there's some struggles because we don't know things, right? But we're going to try and shed at least a little light on that today. While I gave my presentation here a fancy talk about uncertainty, the truth is almost all my talks are about getting the most from your manure. We're blessed here in Iowa. We have a large amount of crop production, a large amount of animal production, and we can really think about manure as a fertilizer resource. And I like to talk about that. I think it's a unique situation in the nation. Not every state is blessed with those conditions where manure really is a value-added product. But here, especially in the Midwest, we get to think of it that way, and it makes my job a lot more fun to talk about it that way. You can find me on Twitter there at Dr. Manure, or if you want to read some random musings about crap, I do keep a blog that I think at least half the time has a joke that's moderately entertaining. All right, so a few things that we're going to try and talk about today. Just manure's role as a fertilizer. We'll review sort of the science behind how we make our manure application decisions. I'll talk you through that really to help set the stage for what uncertainty means and how it impacts those decisions that we're making. Because really that's the heart of what we all do, right? We're trying to help farmers or ourselves make a better decision to get the most from our manure. Especially in times when commodity prices, fertilizer prices have been going up, I think that gives us more flexibility for utilizing our manure, right? It makes those nutrients more valuable to us. And because of that, we can think a little bit more strategically about what fields really need manure. Can I afford to haul it a little bit further? And right now the answer tends to be yes, right? Because phosphorus value is up, potassium value is up. And because of that, sometimes I can justify hauling manure to fields that haven't seen it before. So this is one of my favorite ways to start. This is just a map of animal feeding operations here in the state of Iowa. So every yellow dot you see there is a livestock animal feeding operation that is either a confinement or a large AFO. So open feedlots are on this list as well. And the point here that I really want to illustrate is we do have a lot of livestock production facilities. Sometimes you'll even hear people say we have too much livestock in Iowa. We'll talk through the science of that, but that certainly isn't the case. Now, with that said, we are getting some interesting spatial trends of where these animals are ending up relative to crop production, and I think long-term that's something we really need to think about and what it does for our manure. But despite the fact that some of those areas look pretty yellow, we really are in a position where that manure is a resource in our state. And this is just sort of a history to help illustrate what I was talking about there. And here I'm trying to show you three different things, and we'll talk about each of them independently. The first one there is the blue diamonds, which I'm calling crop capacity. That's how much nutrient, in this case nitrogen, I need to support crop production in Iowa. And by support crop production, I'm really talking about the amount of nitrogen that is harvested every year in our state with the part of the crop that we're harvesting. So in the case of corn, that'd just be the grain, or if we're harvesting some corn silage, how much nitrogen's in the corn silage. A few things to note here. One, I don't take any credit for soybean. I called soybean a legume, so I assumed it would fix all its own nitrogen. The best science I think we have says that that's not the case, but still here in my analysis, I said soybeans don't need any nitrogen. I'm not going to consider them in my analysis. If you think about history and what's happened here, the amount of nitrogen we have needed to support crop production from 1920 to today, right, the amount of nitrogen we're harvesting every year with our crops has increased about 8-fold. Meanwhile, if you think about the manure resources we have, the green triangles there are the amount of manure that I estimate is excreted from the herd of livestock in Iowa. Now, it's not an exact amount because the amount of nitrogen that actually comes out of an animal is dependent on the ration and the diet that we feed it. In this case, I don't, of course, know every ration that's being fed in the state of Iowa, but I do take average nutrient values. I did assume they didn't change with time. That's probably not quite true, but a reasonable assumption at least to get us started. And you see that the amount of manure we have had, while it increased, sort of peaked in the 1970s, and today we're getting sort of back to that level. The 70s was driven primarily by beef cattle production, right? Now, maybe not primarily, but in large part. As we saw the cattle move to the southern plains, we did see a decrease in manure production, and now we're seeing that rise again, primarily driven by increases in hog and poultry production. So we're starting to bring that up. And then sort of that red square at the bottom is what we're really talking about. And that's how much nitrogen I think can get moved from our manure storage out to our field and really be utilized. So I'm trying to correct for how much manure is produced on pasture, the availability of that nitrogen, how much nitrogen is lost during storage, how much nitrogen is typically lost during land application. And you can see that it's a fraction of how much manure is excreted, right? And part of that is because we do have some animals on pasture. Part of that is when you look at estimated availabilities for cattle manure, poultry manure, we're generally only thinking about 60% of the nitrogen as excreted actually making it to available for land application. And it also includes those losses we talked about during storage. So even in a deep pit where we think about that manure being relatively confined, we're certainly not having any manure flow away from us. We still do have volatile forms of nitrogen, specifically ammonia, and we're probably losing somewhere between 15 and 30% of the nitrogen that's excreted. All that serves to reduce how much nitrogen we actually have available. The thing I really want to point out about those red squares, with time you see it trending up, right? So we continue to see that trend, and even though we haven't really seen large increases in the overall amount of manure, certainly in the amount of available nitrogen in that manure, we have seen a trend upwards. And specifically that occurs because we've seen that move from cattle where only 60% of the nitrogen was available, and oftentimes it was raised on open lots where half of the nitrogen was volatilized before land application, to something where we have more availability, oftentimes swine, and because we've started selecting manure storage systems where less of that nitrogen tends to be volatilized. So if you think about the early 90s, before that, we probably saw a fair amount of outdoor storages. We might have called them lagoons or at least earthen holding ponds where we had relatively large surface areas. That leads to more volatilization as we move to deep pits. That tended to decrease that. Even today, we tend to see facilities moving towards a direction where we get better ammonia and nitrogen management within the facility, trying to, in some cases, minimize pit ventilation to minimize movement of air over that manure surface to hold on to some of that ammonia, or in the case of maybe some cattle operations, moving maybe from that open lot sort of facility to more bedded pack or deep pit beef cattle production, where we tend to, again, lose less of that ammonia from volatilization. So the point being really that when you look at how much nitrogen we have available from manure, we've probably increased that 2 to 3-fold over the last 100 years. When we look at crop production, it's increased about 8-fold. So while we do have more manure nitrogen available than most times in history in Iowa, crop capacity has really increased at a much more rapid rate. Because of that, we've never been actually more manure poor. If I think about Iowa and state level nutrient budgets, right now we're getting somewhere between 25 and 30% of our nitrogen, phosphorus, and potassium needs, potentially from livestock manures. Never in history has that been a lower percentage, which is sort of interesting to think about, right? Because we hear this talk about manure is an issue, but really we've never had more crop production, more nutrient need than we do now. Certainly thinking about that at the state level doesn't always tell us the whole story, right? Manures are often relatively dilute when it comes to nutrient content. I tend to think about swine manure being somewhere around 50 pounds per 1,000 gallons. That means we're moving a lot of water around when we try and move that around. And because of that, it gets economically unfeasible to really think about moving manures really large distances. With liquid manures, we might think of 4 or 5 miles as sort of the top. In some cases, we can move a little bit further than that. Oftentimes with solid manures, we might think about 15, 20 miles as relatively a large distance that we might move manures. And when you compare that to commercial fertilizers like anhydrous or MAP for phosphorus, those are relatively short distances. Because of that, I think it's often useful to think about what do manure balances look like at a county level. And that's really what I'm trying to illustrate with these 4 maps of Iowa here. Again, these are nitrogen maps, and what I'm trying to do is compare how much nitrogen I think is available from manure within each county to how much nitrogen is needed or at least removed with the harvested portion of the crops. So if you see a really dark green county, that would mean that less than 10% of the potential nitrogen that we're harvesting with our crops can be supplied from manure. So that's a very manure poor county. On the other hand, if you see a red or very red county, if you see the very red county, that means I'm estimating that more than 100% of its nutrients, nitrogen removed with the crops could come from manures, and red would be 90 to 100%. So each of those colors is broken up by 10% increments. So if we see dark green, that means there's relatively little manure there relative to crop capacity. If we see those red counties, there's a lot of manure relative to crop capacity. Now, a couple things to keep in mind here. Just because you see a county is red, that doesn't mean that it can't utilize all its manure as a resource. I mentioned, and I want to really highlight this, that what I am comparing here is estimated crop nitrogen removal. So for corn, I assume something like 0.8 of a pound of nitrogen per bushel of corn. That's an old USDA number. I do wish that I would change that to 0.6, and I think the next time I try and make a map, I might do that because we've seen at least a pretty good indication that the nitrogen levels in our corn grain have been decreasing. But when you think about that, and especially compare it to maybe what maximum return to nitrogen, which we'll talk about later, or yield goal allows you to put on, it's a relatively small amount. Even at 0.8 of a pound of nitrogen per bushel of corn, yield goal would suggest somewhere around 1.2, right? So somewhere around 0.4 of a pound of nitrogen more per bushel of corn that I'm making. So just because I am showing a county that might be red here doesn't mean that it doesn't have all the land it needs to utilize our manure according to current regulations, and probably even according to best agronomic practices. But one thing you can see relatively clearly in this trend, and I apologize for 2016, it should be 2017 to make all the 7 years, 10 years apart a little more appealing on that map, but I think it really gets the point across is we have seen at least a handful of counties where we've really seen increases in the amount of manure we have available, and it's increased more rapidly than crop production. So we sort of have this segregation going on where livestock are becoming more dense in other places where livestock are becoming less dense, right? And because of that, depending on where you are in the state, we might think about manure a little bit differently. If we happen to be in one of those counties where we think about it as red or having a lot of manure, it might be harder to find fields where it isn't already in a manure plan, where we can really utilize that manure to its fullest extent. If we're in a green county, chances are there's plenty of land available to put in manure plants. It might be hard to find manure if that's the fertilizer choice you want to make. I bring this up because when we think about the manure decisions we make, they're driven by lots of things. Certainly, agronomic practices, environmental practices come to the forefront, but supply and demand is a real issue. So if we have a lot of manure, if it's easier for people around you to get manure from other people, there might be a competitive bid process for how much you're actually willing to pay for manure, even if that manure actually has that nutrient content that you're looking for to supply for your fields. All right, so manure application rate. This is fun because we can really make it as complicated or as easy as we want to. And I like this equation because it makes it look relatively easy, right? If I want to figure out how much manure I need to put on, I only need to know two things. How much nutrient my crop needs, whether that's nitrogen, phosphorus, or potassium, and I probably need to pick the limiting one, and how much of that stuff is actually carried along in my manure, and I'll probably make some adjustments for what's the actual concentration in the manure, how available it is, and how much am I planning on losing due to volatilization at the time of application. And all those numbers are relatively easy to look up in tables, right, or from a history of manure sampling. So I think oftentimes this is the starting place for where we're at, right? This is what the science says. We know this is how much we need, and that's not maybe as easy to come up with as you want it to be. I've mentioned I'm an ag engineer, so I'm going to talk about it at a very elementary level. Many agronomists, I think, and that's a topic that still comes up, is how much nitrogen do we really need? It varies a lot from year to year. It varies a lot with sort of our field conditions around the state. We'll look through a couple methods that we typically use for manure to come up with that number, but I'm not going to hammer that one to death. On the other hand, those three on the bottom there, the nitrogen concentration, the nitrogen availability, and the nitrogen volatilization, those three I'm going to talk a lot more about because that's where I think a fair amount of our uncertainty, or at least the uncertainty differences between choosing manure as our fertilizer or something like anhydrous ammonia, really come in. Okay, so we're going to talk about this in a little bit of detail. Most of you have probably heard this before, but I think it's useful to review so that as we think about where uncertainty comes from, where that variability comes from, we can talk with a common language. So in determining manure application rates, there's really two parts to think about. There's the supply side, and I like to think of that as manure characteristics. So what's my concentration of nutrients? How much of it is going to be available? How much is potentially going to be volatilized because of the application method I'm choosing? How uniform is it going to be across my field, right? It's our equipment and sort of resource analysis. The second part is that demand side, which is how much does the crop need? Now, I don't want to say that demand side is easy. It's certainly not, right? We're going to talk about maximum return to nitrogen, yield goal. I'll talk a little bit about the difference between the two, but I'll leave it at that, and knowing that weather conditions in any given year can make that number much higher or lower. With manures, it's a complete fertilizer. Unfortunately, it isn't always a balanced fertilizer. By that, I mean it comes with nitrogen, phosphorus, potassium, sulfur, and many, many micronutrients already packed inside it, which is great, right? That means one trip across the field, we get nitrogen, phosphorus, potassium, all those things that our plants need to support their growth. The unfortunate or difficult part of that is they don't always come in the right ratios. for what we need. So just because I'm putting on an amount of nitrogen that will support corn production doesn't mean I'm getting as much phosphorus as I need. Or if I'm using cattle manure, maybe it means I'm getting way more phosphorus than I actually need. And if I keep doing this, I might have negative impacts on water quality because I'm really building up phosphorus concentrations in my soil. Because of that, we really have to do sort of this manure application rate calculation for at least 2 nutrients, nitrogen and phosphorus. And I'd encourage you to do it for nitrogen, phosphorus, and potassium, and maybe think about a few other ones. I mentioned potassium specifically because sometimes with poultry manure where we leave it stockpiled, potassium is really soluble. Maybe it's moving through our stockpile down to the soil below it rather than getting redistributed to the field where we want it. So oftentimes it pays to think about all 3 of them, but specifically we're required to do nitrogen and phosphorus, and from a best management practice, those tend to be the 2 that make the biggest differences. So it is what I'm going to focus on in this presentation. All right, so let's talk about the manure side. In manures, there's 2 types of nutrients. There's organic nutrients, and by that I mean it's sticking to carbon, right? So we might think of that if we're talking about nitrogen as proteins, amines, amino acid, things of that nature. And then there's inorganic nitrogen. And when we talk about inorganic nitrogen, that's what you'd normally see in your synthetic nitrogen fertilizer sources. And there we often talk about ammonium or nitrate. In manures, we tend to not have nitrate present when we're doing the application. Now, in some cases with some solid manures, maybe we'll see small amounts of nitrate, but typically the majority of our nitrogen, our inorganic nitrogen, is present in the ammonium form. Typically, I mean somewhere in the neighborhood of 90 to 99% of it will be that ammonium nitrogen and very little amounts of nitrate in it. Now you might be thinking, well, that's a good thing, right? When we talk about water quality, we're often talking about nitrate moving to tile lines or nitrate leaching to tile lines. Now, that's true, but once we put ammonium in the soil, if we have warm temperatures, if we have enough moisture, which we almost always do, we will get some conversion of that ammonium into nitrate where it becomes soluble and can move if water is moving through the soil. Organic nitrogen is an interesting form because plants can't utilize it right away. It needs to be mineralized into that inorganic form, into ammonium, before plants are able to take it up. Bacteria within the soil will again do that. We call that process mineralization, and it can happen at various speeds related to temperature, moisture conditions, and also sort of how easy it is to break down that manure to start with. And you might think about this as a food analogy of things you eat, right? If you eat sugar, that's really easy to break down. It's really quick energy, but it doesn't leave you full very long, right? So it's a rapid conversion. If we think about something that has lots of fiber in it, that is maybe a little harder to break down and a much slower release. So the analogy, when we think about that in terms of manures, if we have a manure that has relatively small particles in it, where we fed relatively high value feedstuffs, maybe soybean meal and corn, like you'd see in a pig diet, we'd expect that organic nitrogen to break down really rapidly into inorganic nitrogen. On the other hand, if we tend to feed a lot of roughage in a diet, or if we tend to use a lot of organic stover as bedding material in that manure, that breakdown might be a little more slow because those chunks tend to be a little bit bigger, right? So bacteria don't have as much surface area to work on them with, and they tend to be more complex stuff that take more enzymes to break down. So they're more of a slow release fertilizer. And we might think about that more as something like cattle manure. So nutrient availability is really a complex topic, right? And as any good extension personnel will tell you, the answer is always, it depends. And in this case, it depends on both the type of manure we're working with, the soil conditions, the moisture conditions, how long we've stored it beforehand, did we do any sort of treatment, solid-liquid separation, was there anaerobic digestion? So there are a multitude of complicating factors. And because of that, every year is a little bit different, right? I think back to a few years ago, 2016, I started getting a fair amount of calls in the early spring from people who had utilized poultry litter on their fields saying that my corn doesn't look very good, it looks yellow, what's happening, what's happening? Well, the spring of 2016 was extremely cold, it was relatively wet, but it was cold. And because of that, that poultry litter didn't break down very quickly. The microbes weren't able to eat that organic nitrogen and turn it into a plant available form. So if you relied on poultry manure exclusively for your nitrogen, early on in that growing season, we probably looked a little deficient in nitrogen. Now, once the soil warmed up a little later in the spring, I think most of those cornfields caught up and looked a little better, but it was something that we saw that year, right? Now, that doesn't mean that nitrogen in the manure wasn't available. We just didn't have the conditions to make it available maybe as rapidly as we wanted that particular year. Other years, we might have the exact opposite conditions, right? We put it on, poultry litter on a little earlier in the fall. It's still warm. We get a lot of mineralization in the fall, and some of that nitrogen can be prone to loss. So the weather is a complicated and variable thing, one that definitely impacts sort of our manure properties. With that said, what we normally tell you to do is look for table values to determine the amount of nitrogen or phosphorus that will be available in any given year. I'm going to show you one graph, and then we'll sort of look at what those tables are. And the point of this graph is really to show you where we're starting at with ammonium relative to organic nitrogen in different manures. And I think that's important because when you see a manure that has relatively high amounts of ammonium in it to start with, sort of that swine lagoon manure, swine pit manure, where we expect somewhere between 80 and 95% of all the nitrogen present to already be in the ammonium form, well, it's going to be really available the moment we put it on in the soil, right? We're not waiting for those microbes to help break it down for us to make it plant available. On the other hand, when we look at that beef feedlot manure or poultry manure, a much greater percentage, generally 75–80% of it, will be available in organic form to start with, and it might take a little bit more time for it to become plant available. And you'll often hear us talk about this in the fall when we say, especially with ammonium-rich manures, it's important to wait until the soil's 50 degrees and cooling before we get it out there and get it applied. That's because if we're putting on ammonium, it only takes one step to turn it into nitrate, which is the form that's available for loss, right? So if we put on swine manure relatively early in the fall, the bacteria are still active. They're going to take that ammonium, turn it into nitrate. If we have any water movement in the spring, and let's face it, we live in Iowa, springs tend to be wet, we tend to have a fair amount of tile flow, we're going to be moving some of that nitrate with that water down into the tile lines and losing it before it can do any good for our crop production. On the other hand, if we start with some of those solid manures, we have to go through multiple processing steps, right? We have to go both from organic nitrogen to ammonium and then to nitrate before it will really move through the soil, and that gives us a little bit more cushion. Now, I say a little bit more cushion because it's not a fail-proof plan, right? If I'm working with poultry litter and I'm out there putting it on in September, well, that's plenty of time generally to get at least some of that ammonium in the nitrate form before we get to spring, right? There'll be enough time in the fall to get that conversion. So timing is important for all manures, but it tends to be a little bit more important, especially when we see ammonium-rich manures. Okay, this table is the Iowa recommendations for nutrient availability. It comes from PMR 1003, utilizing manure nutrients for crop production. If you are working with manure systems to support your crop production, I really recommend this publication. It talks through the basics of how to make good manure management decisions and gives you a lot of good estimates for what availability would be. So we have 3 nutrients listed on here: nitrogen, phosphorus, and potassium. I'm going to save nitrogen for last because it's the most complicated. With phosphorus and potassium, all those numbers say something to 100% first year available. In all cases, we should be assuming 100% availability. Phosphorus, potassium, it is eventually all available. And unless we're working on the cutting edge for phosphorus, where we're trying to be maybe in the below recommendation levels for soil test phosphorus, if we have a field that tests low, then potentially we could think about assuming something maybe a little less than 100% first year available. But with manures, we tend to be putting on more than 1 year of phosphorus to start with, oftentimes 2 or 3 years of phosphorus to support crop production. And because of that, no matter what number you assume for availability, it all works out, because over 2–3 years, it certainly is all 100% available. And if I'm putting on 2 years worth of phosphorus, even if it isn't 100% available that first year, I still put on more than enough to satisfy my phosphorus needs. Now with nitrogen, we talked a little bit about this on the previous slide. We looked at swine manure, specifically deep pit swine manure and lagoon swine manure, and said, well, it's almost all available. It's almost all in the ammonium fraction to start with. That means it should be all really highly available. And if we look at the category here for swine manure, either from an anaerobic pit or an anaerobic lagoon, we see that it says 90 to 100% available. And I think that makes a lot of sense to us, right? We saw it was all in the ammonium form to start with. How could it not be plant available in that first year? When we look at some of the other manures, beef cattle, dairy manure, and poultry manure, we see that number substantially lower. In part, especially with the solid manures, that's related to how much bedding material we have going along with it. We talked about that being a little bit harder to break down. I think dairy manure there is a sort of an interesting case, and one I'm going to pick on this table just slightly with. This table, I think, does a great job giving us a starting point. As long as your manure looks like a typical manure, it gives us right where we should be. But dairy, I think we do some interesting things at. Specifically, we might do some solid-liquid separation. We might have a multi-stage lagoon, and depending on what stage that lagoon we're pumping from for our land application, we might have almost all of our nitrogen available in the ammonium form to start with. It's not uncommon for me to take a dairy liquid dairy slurry sample from the second stage of a lagoon system and see somewhere around 80% of that nitrogen already in the ammonium form. Here we're saying it's only 30 to 40% available in that first year, and I think that's a reasonable estimate if we have a single stage lagoon, we're doing agitation before we're putting it on, and we see a fair amount of that nitrogen in the organic form. On the other hand, if it's a multi-stage lagoon, we're seeing 80% of it already in the ammonium form. That 30 to 40% is probably a little low. I bring this up because while this is a great starting point, I think it puts us generally in the right case. If your manure doesn't quite look typical, I think there's maybe some other things that you might want to think about or consider. Specifically, if I see a dairy manure where I'm starting with 80% of it already in the ammonium form, I'm looking to the old Midwest Plan Service to come up with an estimate of availability. And I'm going to talk us through sort of an example here with liquid swine manure. So when we talked about liquid swine manure, generally I'm thinking 80% of it's in the ammonium fraction, 20% of it's in the organic nitrogen fraction for nitrogen. The Midwest Plan Service method would say all that ammonium has to be plant available. It's already in a form that's plant available, so why would we discount any of that? So with swine manure, that means we're already starting with 80% of it plant available. I'd find what category I'm in here. For most of us, that would be an anaerobic liquid, whether you're in a deep pit or a lagoon. It's certainly an anaerobic system, and it says 35% of that organic nitrogen should be first year available. So if you take that number, take 0.35 and multiply it by 20, we're getting something like another 6-8% available. If I take the 80% I had, another 6% available, I'm looking at something like 90% available, which puts us right at that Iowa State recommendation for how much nutrient is first year plant available. So if we look like a typical manure, what we'd expect it to look, the Iowa State numbers look pretty good. On the other hand, if we're doing something where we might not look like that typical manure, let's say dairy with solid liquid separation so that we have a solid fraction and a liquid fraction, well, we might not want to use that table value because we don't have something that was typical for coming up with what those availability estimates would look like. In that case, I probably want to move towards this Midwest Plan Service to really say what of my percent of my nitrogen in my dairy solids are first year available. And especially on that liquid side, I might say that 30 to 40% first year availability is probably low because we've removed a lot of the carbon, a lot of that organic nitrogen from the mix, and we're focused more on nitrogen that's already first year available. Okay, the second thing we needed to correct for was volatilization. So a couple things to comment on here. We'll often talk about availability, and depending on what state you're in, that might mean different things to you. To me, it means that the nutrient moved to a form where plants could utilize it. On the other hand, if you go over to Illinois and they say plant available, they tend to be talking about how much of that nitrogen would be at least went to a form that was available minus any losses, right? And I think that leads to a lot of confusion maybe when we talk about what availability really means because people are using it differently. When I talk about how much could be used minus any losses, what I'm really talking about is nutrient supply. And that's the second correction that we have to make, and that's nutrient supply due to losses due to volatilization. And volatilization is really an equipment question. So ammonium carries a positive charge. Most Iowa soils will have a negative charge, and that means if we can get that positive anywhere close to a negative, they're going to want to stick together. So when we think about what would help reduce some of those volatilization losses, that means getting manure in contact with the soil. And this table sort of illustrates that, right? If I think about direct injection or even broadcast where I'm doing some incorporation, I'm going to lose almost none of my nitrogen. So if I'm injecting, it says that my nitrogen correction factor should be 98 to 100%. So 98 to 100% of my nitrogen will still be there. I'm only losing 0 to 2%. On the other hand, if I leave that manure on the surface for longer periods of time, looking at broadcast either of liquid or solid manure, I'm going to lose somewhere between 15 and 30% if it's a solid manure, or maybe a little bit lower, 10 to 25% if I'm a liquid manure. So why is liquid manure lower than solid manure? Well, because it soaks into the soil, right? We talked that we want to have that positive ammonia in contact with the soil. If we can get it to flow into the soil, it is soluble, so it wants to move at least a little bit with water until it sticks to something. If we can get that to flow into the soil, it sticks there, we're going to help reduce some of those ammonia volatilizations. One thing to note is these are table ranges, right? There's no one value I can give you because it's dependent on both the equipment you're using, the manure characteristics you have, but also how good of a job you're getting it either covered or how warm and long it sits there before it sort of has a rain that works it into the soil. There's no one right number. If I'm early in the application season, I might pick a little more ammonia volatilization because the soil's warm and it tends to be windy. If I'm late, I might pick a little bit less on that range. When it comes to nutrient contents, you can look up plenty of table values, and in some cases, they still have at least an estimate of how much nitrogen is there. I will say, as these get older and we've modified practices, some of those estimates get really, really bad. So if you think about back to the early 90s, we might have talked about somewhere around 30 or 40 pounds of nitrogen per 1,000 gallons for liquid swine manure. Now I tend to see 50 or 60, mostly due to better water management in the barn. As we moved away from nipple drinkers to either cup drinkers or even better wet-dry feeders, we have less water wastage. Same amount of manure, nutrients being excreted from the animal, concentrations have went up. So the first thing to do is make sure that whatever you're using, if it's a table value, is at least somewhat representative of the system. The other thing to remember is they're only an average, right? And while if I test from enough farms, right, I've done this where I've went out and tested 50 farms here in Iowa, I get pretty close to that average of 50. No surprise, right? If you test enough samples, you're going to get close to what you think the state average is. On the other hand, if I go get a sample from an individual farm, my low is generally 30, my high is generally somewhere around 75, 80. That's a heck of a range, right? Almost double. So if I'm using that book value, I could be off by up to 50% compared to what's probably actually in my manure. So sample, sample, sample is the best way to get a good number there. I know when you sample, you'll sometimes get funny values back. It is one of the challenges taking a good sample. If you think about a pit barn, we're often looking at somewhere around 700,000 gallons in that pit. You tend to send a liter to a lab, and if it's like my lab, most labs are, I'm going to take 1 milliliter of that to run my nitrogen analysis on, right? So relatively small amounts. And that can cause some availability. Did I get a chunk of solids in there? Did I not, right? So I'd like to tell you sampling just once is generally enough. But if you sample every year, which I think is good practice, and you happen to get one value back in a specific year that is either extremely high or extremely low, it helps you say, well, that's not really representative of my system. I've seen this sort of before, and that sort of running average helps us say, this is really what we think is in our manure. All right, I just wanted to run through a quick example of how these table values would work for estimating manure application rate. So let's say we had some swine manure. It's probably from a deep pit finishing operation there, since I set the concentration at 60 pounds of nitrogen per 1,000 gallons. I looked at that ISU table and it said pick somewhere between 90 and 100% available. Here I'm picking 90% available. We do inject most of our liquid swine manure, so I'm saying injection. That means I'm going to retain most of that nitrogen. All I'm doing is taking that 60 pounds times the 0.9 for my availability times 0.99 for my volatilization sort of loss mechanism there, and I'm coming up with 53 pounds of available nitrogen per 1,000 gallons. So supply side really comes down to three factors, right? How much nitrogen do I think is in my manure? Hopefully that comes from your manure sampling test results to say what your manure really is testing. What percentage of that do I think is available, and how am I putting it on, and how does that relate to loss? If we have those three factors, we can handle the manure supply, or at least make a good first estimate of that manure nutrient supply. When it comes to estimating nutrient need, there's two methods. There's the yield goal method, and if you look at manure management plans and the rationale for how it walks you through calculating nutrient need, that's what you're going to find on the form, right? It's going to talk you through that yield goal method. The yield goal method is, at least in your head, a relatively simple method to try and use. It's a mass balance. How much nutrient do I think I'm going to harvest and remove with my crops? And that must be how much nitrogen I need. Now, there's a lot of factors that come into play there, specifically what's the nitrogen content of the crop. I think in general we can do a good job looking that up from a table value. And we also need to know a yield number. And yield number in any given year, we're going to struggle to get it perfect, right? If it's a dry year, if it's a wet year, did I get planted early, did I get planted late? But we can take an average of the last few years, and in Iowa, they say take the average of the last 5 years and multiply that by 110%, and you'll get what you can pick for a yield goal, or take the top 4 of the last 5 years, and it gives you at least a realistic number to shoot for. With that said, we know that no system is 100% effective, so there's a fudge factor we often put in there to say, all right, that's how much as a baseline we need. Now we probably have to put on a little bit more to satisfy our crop need to account for how much nitrogen or nutrient would be lost through leaching or runoff. And that's a little bit harder to do, so those fudge factors, your mileage may vary. And then the second method for coming up with nutrient need is the crop response method. And that's really what the maximum return to nitrogen is based on, right? And so Iowa State University here, we recommend the crop response method. The yield goal method has been shown to maybe not work very well for actually estimating what the ideal rate for nitrogen is. I think in some cases it gives us a nice starting point. But the crop response method really does a better job of saying this is the optimum amount. Okay. So we talked a little bit about the yield goal method, and it really is this simple. You look in your manure management plan packet, they will have this table in there that says how much nitrogen is in different crops. For almost every crop except corn for grain, they give you just a number. You will see soybeans around here. That's for non-nodulating soybeans. We all plant nodulating soybeans, so it's a legume. It doesn't need any nitrogen. In some cases, you maybe put some on for a manure management reason, mostly because we need to put our manure somewhere, and soybeans can utilize that, but it can fix their own, so it's probably not necessary. With corn, we break the state into 3 regions. The very northwest corner there, sort of the Luss Hills, and then the rest of the state. And how much nitrogen it recommends per bushel of corn varies with that geographic location, at least in part due to rainfall amounts, and then a little bit due to soil and yield potentials in those different areas. We talked a little bit about picking yields. They should be based on actually achievable yields, so yield history is a good way to sort of get to that number. The state does allow you to pick either the 5-year average plus 10%, or for the last 5 years. They almost always work out to the same number within a bushel or two, unless something funny happened, like back in 2012 when we had the drought. For a few years, that 2012 number looked really funny, and the 4 of the last 5-year number worked out to a fair amount higher than the 5-year average. But generally, they work out to about the same number. The other thing to think about as you handle sort of the yield goal method is we do need to take credit for legumes. In some cases, I think the legume credit maybe is poorly named. We maybe should call it a rotation effect, because I think most research on soybeans have shown that when we grow soybeans, we tend to remove more nitrogen with the harvested soybean than what they actually fix. But despite that fact, I'm still going to call it a legume credit, because that's what it's called in the manure management plan you fill out. And at least it works reasonably well for correcting for that rotation effect. So with soybeans, we need to take 1 pound of credit per bushel of soybean we yielded the year prior to growing this corn, up to a number of 50. Again, that's probably a rotation effect more than a legume credit from the soybean, but it works reasonably well. If we think about some of the other systems we might have, specifically those where we're growing some alfalfa, that is a really good legume. How much nitrogen credit we should take is really dependent on a lot of things. What's the quality of that alfalfa stand? Did I harvest it 3 or 4 times? How much of it is left sort of as a green manure when I was growing it? If you have a really high quality stand of alfalfa, we can take somewhere between 100 and 140 units of nitrogen per acre as potentially available the next year. When you think about what that means, that is almost enough to supply many of our corn crops with the amount of nitrogen they actually need for production here in Iowa, or at least half of it, right? So a fair amount. If we have a little bit less quality stand of alfalfa, we're going to take less credit. When we think about the corn response to nitrogen, it's all based on yield trials, years and years of yield trials at numerous sites across the state. In Iowa, they've done these trials with 2 different rotations, either corn following soybean or corn following corn. We put on different rates and say, how much more corn do we grow when we put on a little bit more nitrogen? Take all those and average them together, and you can get sort of curves that look like this. And what we're looking at there on the y-axis is an increase in yield, right, for every bit more nitrogen that we put on. Now, a couple things I want to point out on this. Not surprisingly, corn after corn has a greater increase in yield from that next unit of nitrogen than corn after soybean. That should make sense to us, right? We talked about that rotation effect, or that legume effect. Corn after soybeans gets some residual nitrogen in the soil because we grew soybean the year before. So that sort of buffers how much nitrogen our crop needs, and because of that, the yield response curve is a little bit flatter. Now, the important part of this corn nitrogen response method is Iowa State already has a calculator built for us. All we need to do is go to the web page and look for it. If you type in corn nitrogen rate calculator, Iowa State, it will come up with a web page that looks something like this. You enter in what you estimate for the nitrogen price, what you estimate corn price will be, and it will come up with a rate recommendation for you. If we look at that graph on the bottom, it's really looking at 2 different things here. That top blue line is sort of how much yield it's estimating we're making. And really, we looked at that yield response curve, and it's saying that as we add more nitrogen, we're going to get a little bit more corn yield, but as we add more and more nitrogen, how much extra corn yield we get decreases, right? The law of diminishing returns. And that sort of makes sense. As we have plenty of nitrogen in the soil, something else becomes our limiting factor, whether that be water or growing degree days. Something else will become our limiting factor, and we just can't get that much more corn just because we're putting on more nitrogen. And then that green line on the bottom is just our cost of nitrogen, right? So it goes up for every extra unit of nitrogen we put on. We had to pay whatever we're paying for nitrogen, generally somewhere around 31 to 50 cents, depending on the form and how much we're selling nitrogen for. If you take that blue line minus the green line, that gives our profit or partial profit budget response. The important part of that partial profit budget response there is there's a maximum to it, and that maximum is the amount of nitrogen that we'd put on to get as much profit as we could. And then the calculator spits out that number, right? In this case, it looks like it was somewhere around 134 units of nitrogen per acre. And then it gives us a range where we'd make within $1 profit of that number. So there is some flexibility in that. And that should make sense to us. This is an average. And if you think about any given year, I'm not very good at picking that number. But if I'd average 2 or 3 years together, I'm probably pretty close to that average. If I average 20 or 30 years together, I'm probably really close to that average. So in any given year, there might be some flexibility because different weather conditions are different. And the range there maybe lets you say, if I think it's going to be a really good year for corn production, maybe I need to be on the higher end of the range, or maybe I need to be in a drought year on the low end of that range. And that's a decision that offers you some flexibility based on the weather conditions you're seeing. So just an example to figure out what our rate was. If we think back to that manure we had earlier, it said we were going to have 53 pounds of nitrogen available per 1,000 gallons, right? Because we were injecting and it was liquid swine manure, 90% available. The maximum return to nitrogen tool there said in a corn-soybean rotation, I need 134 pounds of nitrogen per acre. So all I'm going to do is take that 134, divide it by the 53 that's available, multiply it by 1,000 because I'm working on everything per 1,000 gallons, and I need somewhere around 2,500 gallons per acre. Okay. That was the fun part, right? That was sort of the review. Now we're going to talk about variability uncertainty and how it impacts that decision that we just said for the rate that we should be taking. Now, with manure, there's lots of things that we aren't always perfect with. Manures are, at best, uncertain. At worst, they might be filled with 2x4s, bits of concrete, and all sorts of things that plug up our application equipment. So, what are some of the things that cause us to maybe not be as great about application as we want to be? And I'll give you a list here. Our ability to hit rate, knowing how much nitrogen our corn actually needs in any certain year, the nutrient content, both how much is actually in our manure and how does it vary from the start of a pit to the bottom of a pit, right? The nutrient consistency. Availability, right? I'm giving you a table value, and for swine manure, I said it's somewhere between 90 and 100%, but what was it this year? Or volatilization losses, or even uniformity across the toolbar. And all these things add up and say they impact how much nitrogen we really put on that's available to our crop compared to what we were shooting for. Okay, so we're going to try and talk about a few of these, and I have some data. This chart happens to come from data up at Nashua, Iowa, where we are utilizing liquid deep pit swine manure for our fertilizer source. We did some sampling, and then we said, this is how much nitrogen we're trying to put on, what my target rate for application is. And what you can see here is when I look at how much nitrogen I was trying to put on, which is in that left-hand column there, somewhere between 112 to 224 units of nitrogen per acre, in this case, kilograms of nitrogen per hectare, sorry, I'm in a terrible unit for us there, compared to how much I put on, it wasn't uncommon for me to be off by 20%, right? Either 20% high, 20% low. So despite the fact that I am pre-sampling my manure, I think relatively well, that I'm only putting manure onto 1 acre plots, so I have a fair amount of ability to control and hit the target rate that I'm putting on. It's not uncommon for me to miss my target rate by 20 to 30%, right? So a ways off. Now, that could mean in some years I put on extra nitrogen. That's just wasted nitrogen that I didn't get to use on a different field. In some places it might mean that I was short of that nitrogen, my corn looks a little yellow, and I'm a little disappointed in what my yield actually was. So why did I miss my rate? There's a couple reasons that you can miss rate, right? The first one here is nutrient content. And what I'm showing here is what my pre-sample nitrogen content was compared to what it was the day of application. And the day of application, I take a sample from every tank load where I do a 1 acre plot. So I have a lot of samples the day of application. And what we tended to see here was that on the day of application, our nitrogen content tended to be about 20% lower than what it was when we pre-sampled. Why is that? I have no idea. I've done this on numerous farms other than this one, and I almost always come up with the same number or something that's reasonably similar, right, within 5 to 10%. In this case, this farm, for whatever reason, it was consistently different. Now, I will admit I didn't agitate at the time I pre-sampled, but at the other farms I don't either, and for some reason this farm gives me tons of trouble. So, despite the fact that I work at Iowa State, it wasn't a nice manure to me. It was rather unpleasant, and for some reason, we saw that consistent change. So that was at least a big part of why I was missing my rate, right? I was using my pre-sample to calculate it, and the day of sample just wasn't represented very well from that. Later on, I did adjust how much I was putting on because I knew I was consistently wrong. The other column I want to point out here is the second one from the right. So the day of application sample CV. So that's my variability from load to load. And I point this one out because I think it's an interesting column to look at and think about what's the variability of my manure as it comes out of a storage, right? And what I saw was somewhere between 5 and 10%. And that one's an interesting to us because we're seeing people introduce new technologies where we can real-time measure nitrogen concentration and maybe adjust on the fly. So if we have a 5% variation in nutrient content of the manure, what does that mean for value? Well, I'll talk about that in detail in just a few more slides. The other part of that equation is, am I actually hitting the rate that I said I wanted to put on? And in this case, we are using a Raven control system. I think that's pretty standard. Some of you might be using something else, either the John Deere Case or the Ag Leader systems, but they all work with the same premise, right? We have some sort of flow meter up there on our tanker or in our dragline system, typically a Krone flow meter. The manure flows through there, it takes a volume reading, and then we have something that helps us adjust that flow rate, whether it be adjusting the speed of the pump, adjusting the speed of the tractor, or in some cases having a valve that helps open and close and throttle how much flow we're actually getting. In our case, on single acre plots here, we generally did a pretty good job of actually hitting the volume of manure that we said we wanted to apply, right? Somewhere between 0 and 5%. These are 1 acre plots. That makes it easy in some ways, right? I can do a whole plot with just a single tanker load. I don't have starts and stops. I don't have that variation in application volume as I'm sort of trying to hit where did it end up, where did my last load stop. But I do have that startup and stopping on each plot where the warm up and cool down of that sort of flow from my pump is hurting me and hindering me hitting rate. I don't have a dragline system, right? I don't have end rows to contend with, so I'm not sort of double applicating on the end rows and trying to adjust my speed. So I do have a pretty nice system for hitting rate there, but I think in general, that's about where we'd probably see most fields, somewhere in that 0 to 5%. And maybe in some cases, especially fields where we're draglining with lots of end rows, maybe we'll be a little bit more off than that. But from what we saw, it tended to be more on the estimating nutrient content than application volume in hindering our ability to hit the actual total amount of nitrogen that we wanted to hit. When I look at what this was costing me, right? So in every year I could say, how much extra nitrogen did I put on if I valued nitrogen at something like 31 cents per pound? How much value did I lose because of over-application of nitrogen? Or if I use that maximum return to nitrogen yield curve, I could say how much short am I on yield because of not getting the amount of nitrogen I wanted to put on. And generally we found somewhere around $30 to $40 per hectare of value from that. If you think about that in terms of dollars per acre, me missing rate was costing me somewhere around $15 per acre of potential value. So if we think about better equipment, better technology, that's really the amount of money we're potentially chasing, right? Somewhere around $15 per acre of better management available to us. This is just another way of looking at the variation during nitrogen application, right? So on the x-axis there, I have the coefficient of variation, which is just the standard deviation divided by the average. So it's sort of how much percent variable it is. So if it was 100% variable, that would be saying something like it's anywhere from 0 to 100 if the average was 50, right? We tended to see variation somewhere around 20 to 5%, with the variation tending to be smaller as nutrient concentrations got more concentrated, which is what I'm showing on the x-axis. Okay. There's nothing super important for you to know necessarily about this figure, other than I need that data to figure out how much value that variation is adding to me. So if I'm over applying, I assume value is the cost of wasted nitrogen, right? That's nitrogen I could have used somewhere else. If I end up under applying because my manure actually has less nitrogen than what I was estimating, that's lost yield. There's a technique called Monte Carlo simulation, which is what I used here to figure out what potential value I could collect from a system where I'd really know how much nitrogen it is rather than estimating one time from a sample. So what I did is I basically randomly pulled what the nutrient concentration of the manure would be from a normal distribution that had a certain average and a variability based on that figure I just showed you. So if you do all that, run it through my Monte Carlo model, and then say, what does that really mean for value? You can make a figure that looks something like this. And what I'm showing on the x-axis is the manure nitrogen concentration, again, in this case in kilograms per cubic meter, which is an interesting unit, but I should have put it in pounds per 1,000 gallons, so I apologize for that. I will say that somewhere around 50 there is roughly 50 pounds per 1,000 gallons. It works out to about the same number. 20 is a little bit lower than that. It would be something like 10 pounds per 1,000 gallons. And then on the y-axis there, I have values again in dollars per hectare. If you divide that by 2, that would turn us into dollars per acre. I have to make two curves here, one for corn following corn, one for corn following soybean, because missing nitrogen rate is more valuable in a continuous corn operation because we saw that yield was more impacted by nitrogen application in a continuous corn system. A couple things to note then. As the nitrogen concentration gets higher in the manure, there's less value for getting the real-time measurement correct because we saw less percent variation in the nutrient concentration, right? It was more consistent, somewhere around 5% variation. In those cases, whether we're in a continuous corn or corn soybean rotation, it's worth somewhere around $10 to $15 per thousand, or $10 to $15 per hectare, somewhere around $7 to $10 per acre of potential value if I was measuring the real-time nutrient concentration of manure rather than just using one consistent number from a sample I sent off. As we get lower nitrogen concentrations in our manure, maybe something that we'd see at a farrowing or gestation operation or at a dairy farm, those values tend to go up relatively quickly, right up to $30 to $50 per hectare, somewhere around $15 to $25 per acre. So as you think about whether or not you want to put these systems in, how much value can you gain from them, we're really looking at the neighborhood of somewhere around $5 to $10 per acre of recovery of costs if those systems are getting the nitrogen content right of the manure, right? So that's assuming it gets 100% right. If it's 90% right, these values would be reduced at least a little bit. So what about some of those other variations that we might encounter? So manure injection, right? And the truth is, I staged these photos, right? This is all from the same field, same application equipment, same day. The picture on the left, that manure injection looks really good, right? I'm there 5 minutes after I put manure on. I can't find any drops of manure. There's still lots of residue. I got the dirt on top of that manure injection band really well. I probably have minimal ammonia volatilization. On the other hand, on the right, that's 30 minutes after they've been through to put that manure on. It's still sitting there. That's from the end rows. It's really compacted there. It's hard to get good coverage. But in that part of the field, we still see that manure sitting there. It's definitely more available for ammonia volatilization loss. We're definitely getting more loss. And the point being, variability in our field and how well our equipment is working, how well our equipment is actually doing injection from field to field can happen. And it's important for us to be mindful and pay attention to that and make adjustments to try and do a better job where we need to. In this case, that might have been pre-working the end rows so that we could actually get that coverage unit to do its job for us. When we talk about variability of manure coming out of the pit, there are some things we can do, right? We can try and do better agitation, especially with swine deep pits. I know we tend to be in a hurry. To have that manure uniform before we start, it probably takes 3 to 4 hours of pre-agitation before we start pumping that manure out. That's not always the case. If we move to dairy manure storages where we have a much larger storage volume, it's really hard to get that manure as uniformly mixed. We tend to see some increase in solids content from the manure from the top of the pit to the bottom of the pit. And with that, we tend to see some nutrient content variation, generally much more so on the phosphorus side than the nitrogen side, but it does impact nitrogen as well. I'm showing this mostly because I worked really hard to make a pretty picture. I think we've done a really nice job of getting better rate control. I think we're doing a much better job at hitting those target rates. Certainly we still have some challenges with end rows, turnarounds with dragline systems, starts and stops with tanker systems. But as you saw in our plot data, we were generally within 5% of hitting the target rate we were aiming for. That's pretty good. The other thing to think about on hitting rate is how uniform is our manure across that toolbar. All right, so that's what this picture is trying to illustrate. Almost all manure spreaders or dragline systems have a manifold of some type where we're splitting that flow out to each of the toolbar points. Here's just a picture of what that might look like. And this is exactly what you want it to look like, right? Of course not. When you look at this picture, you see that there's a lot of flow coming out of the middle, sort of points there, much less flow coming out of the ends. We're not very uniform across the toolbar, and that means some of that corn might be getting more nitrogen than it needs, some might be getting less. We looked at a fair amount of different toolbars here. This is just one on a couple different tankers, some different styles that we have available to us. I want to talk to you a little bit about what this means to you. Again, I use that yield response curve because it gives us a nice way to think about how much yield is impacted by it and what would happen if I had a manifold that had 15% variability between knife to knife, 10% variability from knife to knife, sorry, or something where I had 35% variability from knife to knife. And then I'm showing each of the knives up there and how much nitrogen actually came from that knife. So if we're thinking about the system where we had 35, it looks like my worst knife there had 70 units of nitrogen per acre going to that corn row. My highest knife there had somewhere around 220. If I look at where I cut that variation down to 10, it looks like my low row there is somewhere around 120. My high row is somewhere around 170. If you think about what this means for corn yield, again, I have to split it out between a corn-soybean rotation and continuous corn. In a corn-soybean rotation, it's costing me somewhere around 2 bushels an acre to go from 10% variation from knife to 35. In a continuous corn operation, it's costing me about double that, 4, all right, to go from 10% to 35. So what's some real variation we see on some of these distributors? This is a manifold. It's based on a hydroflow design. There's a hydraulic pump on the top. It has some knives that spin around in there that block those outlets periodically. And we can see it did a pretty good job, right? It had less than 10% variation from knife to knife in general. Almost all the manifolds that we looked at that were this similar style performed in that reasonable range. On the other hand, this is that same general style, but they didn't have those outlets all the way around. They stopped having outlets on the back side, so they're on the front side. Symmetries are friend on this because of how it's blocking those knives. In this case, it doesn't block them all uniformly. As we drop that flow rate down, right, we have less pressure in the manifold. We see a lot more variation from knife to knife, in this case up to 50%, right? So a substantially higher variation from knife to knife even than that 35 that I mentioned earlier. I want to just hit on timing a little bit, right? We talked about some of that, how timing, especially with high ammonium manures, is really important. I have 4 treatments here that I want you to think about. The first one on the left there, that's spring UAN. It was a chisel plowed system, so that is the only one that gets a tillage application into it. All my other 3 treatments are no-till, so there is a catch here about what I'm actually doing, right? But that is a spring application, and I average somewhere around 240 bushels per acre of yield. When I did early fall manure, early fall to me in this case was roughly the beginning of October. Again, with the no-till, it was injected manure. I only averaged somewhere around 160 bushels an acre, right? If I went to early fall and put cover crop, I did get a little bit more on average, somewhere around 165 bushels per acre. And if I could wait to late fall, that's somewhere around the early November to me, where the soil was roughly 50 degrees and cooling, I got up to almost 200 units per acre on average. So moving from early fall to late fall definitely gained me a fair amount of yield potential, right? Roughly 50 bushels an acre. And then in this case, if I was potentially maybe able to move from fall to spring, I could have done a little bit better. I do have some continuous corn data. The other stuff was corn soybean data to illustrate that. So here I have, again, a late fall manure with instinct and a late fall manure. I got a nice yield response from instinct. This is in continuous corn. So with late fall, again, roughly that beginning of November, I was somewhere around 175. If I put instinct in with that manure, I was roughly just a little under 200. And then if I would move to continuous corn, I was up to 225, right? So gaining another 35 bushels an acre. I just wanted to show you that timing does make an impact. Okay, so we talked a little bit earlier about that Monte Carlo simulation, and we said, well, this is really easy, right? Manure application is just these 4 factors: my crop yield and sort of how much nitrogen in my manure and my variability, and then we talked about all these places of uncertainty. I can plug all those into sort of this model and say, how much should I really be putting on, right? And I came up with roughly 4,000 gallons an acre. But then if I take each of those factors, make a normal distribution from them, pull from them, I can say, well, how does being wrong impact me? And if I have this uncertainty, how does it change what my ideal rate should be? And I tried to do that, and I came up with this figure for you. And on the x-axis here, so the bottom, I have knife-to-knife variation, right? So the coefficient of variation between each of those injection points. On the y-axis, I have how it impacts what my maximum return to nitrogen application rate would be. So a couple different things down here. I have both spring and fall, and then I have continuous corn and soybean rotations to think about. So when I was trying to adjust for fall versus spring, what I did is I said that by putting it on in the fall, that's going to cost me 15 pounds of available nitrogen from my manure. Now you would think that that means that in my fall application, my maximum return to nitrogen would be 15 pounds of nitrogen per acre higher than my spring application. Unfortunately, that's not the case, right? Because I have a variation about that number. It might be 0 in some years where I effectively have no leaching. It might be 40 or 50 in some years where I have more leaching. Because of that, despite the fact that in this case I had a good average for how much nitrogen I thought I was going to lose, I had to put on more nitrogen to make up for that, showing the importance of timing, right? That uncertainty really impacts us. So instead of just that 15 pounds that I lose on average, it was saying I needed to put on 20, 25 pounds of more nitrogen to make up for that number. The other thing you can see here is that variation, just that uncertainty and how much of it's really available, how much of it is actually volatilized, all caused an increase in what my ideal application nitrogen rate would be. So in this case, we should have been somewhere around 150 based on the crop and fertilizer nitrogen price that I input. But no matter how variable my knife-to-knife was, I was told, based on my Monte Carlo simulation, to apply 8 to 10 pounds more of nitrogen per acre with manure because of those that variability and that uncertainty in the parameters that I needed to estimate. Okay, so a few things to leave you here with today as you think about uncertainty, variability of manure, and how it impacts the decisions that we're making. So at our research site, misapplication was costing us somewhere around $14 per acre with deep hit swine manure. So that's value we could potentially improve on if I can come up with systems that help reduce either some of that variability or that uncertainty in hitting actual application rate. When you correct deep pit swine manure application rates for the uncertainty and variability we see in typical application equipment available to us today, our ideal rate is somewhere around 15 pounds higher than what it would be just from maximum return to nitrogen. If we're moving to fall application rather than spring application, we need to increase that a little bit more, because application timing has a huge impact on yield, as you saw through some of our yield data. With that, I'd like to thank you for your time. I certainly enjoyed talking through manure with you today. If you have any questions, please do feel free to email me at dsa@iastate.edu, or you can give me a call and I'd be happy to talk about it with you at 515-294-4210. With that, thank you and have a great day.